Thanks, Lindsay. Let's see if I can advance. There we go. So a couple of ground rules here. Lindsay had mentioned submitting comments through the chat feature. I'm probably not going to be monitoring that through the presentation. So we'll take a look at all those at the end. Participation obviously is required to receive PDH credit. There are some questions throughout. The questions are timed. Just submit the question or submit the answer when prompted. And probably the most important one is if you do want PDH credit, you need to be registered. So if you're in a room with 4 or 5 other people, watching this, really only one person is gonna get the credit unless you're individually registered. So I'm gonna have a brief introduction on concrete, the bread of the construction industry, 5 essentials of quality concrete. Then we'll get into cold weather concreting. It's really going to be most of this information, and really comes out of 2 ACI documents, 306 and 306.1. At the end, we're going to talk about the maturity method, ASTM C1074, which is a non-destructive way of estimating concrete strength. So the bread of the construction industry, concrete. When you think of bread, it's kind of a dietary staple, kind of similar with concrete to the construction industry. It's widely used. It's kind of a staple of the construction industry. It's the second most widely used material in the world, next to water, and a lot of water goes into concrete. Here we've got kind of a general makeup of concrete by percent, obviously percent by volume, 6% air. This can obviously change depending on the application of your concrete. About 11% Portland cement, 41% gravel, crushed stone, that's your coarse aggregate, 26% sand or fine aggregate, and about 16% water. Again, these are just general numbers. It's going to be, it'll be different, just depending on the mix that you're using and what the application is for. But I like the term, the bread of the construction industry. I didn't coin that myself, but I think it's fitting. Pretty much all the ingredients in concrete are right here in front of you, other than maybe some admixtures, for the air, or controlling the slump, or changing the slump, or something like that. But similar to bread, bread doesn't have a whole lot of ingredients, but each one of them is important. And just like bread, concrete, you got to have some quality materials going into it. The materials need to be suitable, compatible with each other. Some admixtures are not compatible with each other. Some aggregates are not very compatible with cement, and they can react negatively and cause problems. So you want suitable, compatible materials. It's got to be mixed properly. It's got to be proportioned properly. Again, the mix specific to the application, interior, exterior, high performance concrete, lightweight concrete, whatever the application is. It's got to be proportioned, mixed, and transported. A lot of people don't think about the transportation of concrete, but there's some places in the Adirondacks where concrete plants are not nearby, and you might have a long transit time. So that should be taken into consideration. Placement and consolidation. Obviously, it's got to be placed, consolidated properly, and then after that, you've got finishing. If it's flat work, jointing. If you got construction joints or control joints or whatever, to control your cracking, and then you've got to cure it. After you're done finishing it and joining it, just walk away. You gotta cure it and protect it properly. which is a lot of what we're going to be talking about today. So cold weather, what is cold weather? How is it defined? ACI has a couple of different definitions for it. ACI 306.1, I should have pointed out, I mentioned the presentation is based on ACI 306 and 306.1. 306 is a guide to cold weather concreting, and 306.1, those are the ACI specifications for cold weather concreting, and they can be incorporated into your project just by reference. But 306.1 defines cold weather as 3 consecutive days where the average temperature is below 40 degrees, and they just take the average as the high and the low. That's it. It's not a weighted average or anything like that. It's just the high and the low for the day. So average below 40 degrees and less than 50 degrees for half of any 24-hour period. So it's kind of weighted to a certain extent by that, but not necessarily. And then 306, the 306 definition is when air temperature has fallen to or is expected to fall below 40 degrees during the protection period. So we see that 40-degree temperature is certainly a common theme here. Probably the most common definition is that top one. That's the one that we see a lot of times in specifications, or maybe other agencies, DOT, New York State DOT, or other agencies may have different definitions of cold weather when placing concrete. But these are the two definitions that ACI uses right here. So why are we talking about it? I don't know where everybody's at right now. I'm in kind of upstate New York, just outside Albany. Starting to get cold. It's been relatively warm recently, but starting to get cold. Construction doesn't stop when it gets cold, and there's a lot of ways that that we can safely place concrete and still have it be durable. Make adequate strength and be durable. So here's a project that's local to the Capital District, Albany area. This is Rivers Casino in Schenectady. This was done, geez, I don't know, maybe 7 or 8 years ago now. But you can see this was done in the wintertime, and I'm going to be referring to a lot of pictures from this project because the team did a pretty good job with cold weather protection on this one. Here's another project. I think this is, I didn't take these pictures, but I think this is in Ticonderoga, up around Lake Champlain. You can see it's obviously wintertime. I'll show a couple more pictures of this project also. So 306, ACI 306, again, that's the guide to cold weather concreting. Objectives, main objective, prevent early age damage due to freezing. We want to ensure adequate strength gain development during and after construction, certainly during construction. Maintain curing conditions that promote strength development. We want it to make strength, obviously. Get within 15 degrees of table 5.1. I'll talk about table 5.1 here shortly, but table 5.1 has got minimum placement temperatures. There's a maximum placement temperature also. ACI doesn't, they recommend that you not be more than 15 degrees above the minimum placement temperature. So there's not a very big window in there for placement. Again, that's in 306R. Limit rapid temperature changes, which may cause cracks due to thermal stress. We'll talk about that. And providing protection consistent with the design and durability of the structure. So these are all the objectives in 306R. Again, 306R is the guide to cold weather concreting. It's not a specification. It's just a guide. It's got a lot of really good information in it. I think it's only like 30 or maybe 35 pages long. It's a pretty easy read, and I certainly recommend reading it is a lot of good information. So preventing early age damage, probably the most important thing is protection and planning. Planning for sure, you know, that it doesn't just happen organically. So preventing early age damage, about 500 PSI will provide us one cycle, one freeze thaw cycle of protection. And we can usually get 500 PSI within 1 or 2 days after placement at about 55 degrees. That's a general guideline. Again, that's going to be specific to the mix. If you've got multiple freeze thaw cycles, that 500 PSI certainly isn't going to hold up to that. But one freeze thaw cycle at 500 PSI shouldn't see anything harmful. It's obviously vulnerable to freezing when it's critically saturated early on. The concrete's still got a lot of water that hasn't, the cement hasn't hydrated, and that critical saturation point, you know, that's the degree of saturation where one freeze thaw cycle causes damage. That's how ACI defines the saturation point. So prior to placement, these are ACI 306.1 requirements. So if your project or if you're referencing 306.1 in your project, you know, these are all part of the specifications in 306.1. Concrete's got to be air entrained if it's exposed to freezing and thawing during the construction period. A lot of people don't think about that, but if you've got flat work, interior flat work that's being placed in the middle of the winter, obviously it's going to be exposed to freezing and thawing, or certainly could be exposed to freezing and thawing. That really needs to be air entrained to protect it. People out there are going to scream and holler about the slab peeling up and not being able to finish properly. It could cause finishing problems, but as long as the finishers and people doing the flat work know that it's air entrained, it can be handled properly. Minimum temperature of massive embedments needs to be 32 degrees. Massive embedments really isn't defined very well in 306.1. Large anchor bolts, you know, things like that, you know, just those large steel embedments that are going to retain a lot of cold. You know, obviously concrete's not going to bond to you know, frozen rebar very well, if at all. Thawed subgrade's got to be thawed out, and frost has got to be removed from all reinforcements. So those are all the requirements in 306.1. There's obviously more requirements, but those are some of the big ones. This is that project in Ticonderoga. You can see they kind of protected it a little bit from the wind. You can't see any heaters in here, but there are heaters in here. There are glycol heating lines, so you see these are glycol heating lines. This is a blanket. They had a blanket over the subgrade, heating the subgrade overnight, and you can see they're placing the slab over here. So subgrade was thawed. They've got a little bit of protection in there, a little bit of heat, and then they're going to put those blankets back on and you know, protect the slab after it's placed. So this is kind of a condensed table from ACI 306. I'll be referring back to this, or it's going to be mentioned a couple of times. This tells us what the minimum concrete temperature should be as placed and maintained. You know, 55 degrees. It's got right here we've got two columns. One where your minimum section size is less than 12 inches. So this is, you know, your 8-inch foundation wall or 6-inch slab or something like that. And then this column is where your minimum dimension is 12 to 36 inches. So maybe this is, you know, an 18-inch foundation wall or a 24 by 24 pier or something like that. This table does extend, so you know, there's more columns for I think 36 to 72 inches, and then maybe even one for greater than 72 inches. So it does cover mass concrete to a certain extent. But again, minimum concrete temperature as placed and maintained. You know, for those smaller elements, 55 degrees. Larger elements, you can go a little bit colder. You're kind of using the heat of hydration. You know, when the cement is hydrated, it's an exothermic reaction, so it kind of creates its own heat. So we're kind of using the heat of hydration to our advantage. These next three lines, 2, 3, and 4, these are the minimum concrete temperatures as mixed. So if your ambient air temperature is above 30 degrees, again, you know, we're still in a cold weather situation. You know, minimum concrete temperature is 60 degrees. If it's above 30, 0 to 30, 65 degrees below 0, you want that concrete temperature to be 70 degrees. This is where that 15 degree maximum comes in. It's not listed in this table, but it is mentioned. You know, you don't want to heat the concrete up to 100 degrees just because it's cold outside. You know, that could cause other problems. So, you know, the recommendation in 306 is to you know, mix within 15 degrees of this, or no more than 15 degrees higher than these temperatures, or these if you're you know, in these larger sections. So how do we heat up the concrete in the dead of winter? Well, we can heat up the aggregate, we can heat up the water, we can heat up the cement. This gives us, I think this is from the Portland Cement Association, this just gives us an idea how much of a mixed temperature rise we can expect with rising material temperatures. You can see the slope of this curve is a little bit steeper for the aggregate. Heating up your aggregate is going to give you a lot more bang for your buck, maybe, you know, like a 2 to 1 or 1 to 2 temperature rise for every 2 degrees. In temperature rise for your aggregate, you'll get maybe about a 1 degree temperature rise in the overall mixed temperature. You can heat up your water also. It's a lot easier to heat up water. It's not quite as efficient when it comes to the overall temperature rise. You can heat up the cement too. I don't see that happening very often, but maybe if you got a fresh batch of hot cement, that might help you, but could cause other problems also. But definitely the aggregate, heating up the aggregate is going to give you the most bang for the buck. Heating up the water is usually easiest, but this graph just gives you an idea of what you can expect. So here's the first question. Should be a true-false question. It reads true or false, ACI allows concrete to be placed on frozen subgrade. Hopefully everyone gets this right. I see all the answers also. So if there's anybody out there that I know that gets the wrong answer, you might get a little jab from me down the road.
All right, poll is closed. Back to you, Steve.
All right, that of course is false. All right, protecting for strength development. We have a protection period. The protection period, again, this is 306, these are the guidelines. Protection period can vary. It can vary, you know, based on what's being placed, and the type of concrete could vary by other factors also. But These are the recommendations from ACI for number of protection period, or a number of days for your protection period. It's kind of based on the service condition. This service condition, where it says load, no load, the load is during the curing period. So that's, during the first 28 days. And the exposure is based on its service condition, not the curing condition, but the service condition. So no load, not exposed. This is, no load during the curing period, and not exposed. The exposure is freeze thaw exposure. So this first line here, no load, not exposed, that could be, maybe a footing, that's down below the frost line. That's really not going to see much of a load during the first 28 days. And then in its service condition, it's, hopefully down below the frost line. So for normal concrete, we've got that protection period is 2 days. If you've got accelerated set concrete, maybe you've got an accelerator in the mix, or maybe you've got type 3 concrete, that protection period is only 1 day. No load exposed, we go up to 3 days. Partial load exposed, we're going up to 6 days. This partial load, maybe that's a pier that is, you're going to start erecting some steel or something like that on a pier. That's going to be a partial load. It's obviously not going to be a full load, but it'll be a partial load. And that pier, maybe that pier is exposed to freeze thaw. Line number 4, full load. The ACI 306 refers us to Chapter 8. We'll come back to that. Chapter 8 basically talks about different ways to non-destructively test the concrete. And again, we'll talk about that a little bit more. So how do we protect the concrete? What's the best way to protect it? 306 gives us a lot of information on protecting the concrete, how to protect it, what kind of protection we need, and it's using the heat of hydration to our advantage, so as after the concrete's placed, we want to keep all of that heat in the concrete, whatever was placed and formed up. This is a table in ACI 306 7.3.2. I think this is 306, the 2010 version of 306. In 2016, they changed it up a little bit. The information stayed the same, but the tables changed. The layout of the tables changed a little bit, and it just didn't present as nicely. So I kept this version from 2010. So what this particular table is telling us is what R values, what R value we need for different ambient air temperatures. And this is assuming that everything was placed at 50 degrees. That's at table 5.1, placed at 50 degrees. And assuming all these conditions are met, in theory, it should maintain that 50 degree temperature for 3 days if we're doing all of this. So this column here on the left side, this is the wall or slab thickness. So we've got 6, 12, 18, 24, so various thicknesses. Each one of these sections is for a different cement content. So this section right here is for 300 pounds per cubic yard. This is for 400 pounds per cubic yard. The one I've got highlighted here is about 500 pounds per cubic yard. The mixes we see these days are typically 500-600 pounds of cement per cubic yard for 3,000, 4,000 psi cement. So let's say we're placing concrete and we anticipate the ambient air temperature to get down to 3 degrees, so single digits, 3 degrees during our 3-day protection period. We've got a 12-inch foundation wall. Again, 500, our mix has got a minimum 500 pounds per cubic yard of cement. We've got 12-inch foundation wall. Our temperature is going to get down to 3 degrees. This R value of 6, if we protect it, in theory, we should be able to keep that 50-degree Fahrenheit for 3 days. So that's how this table is used. Very, very useful in the field for, inspectors, contractors, engineers visiting a job site during cold weather. This is a great table. There's multiple tables. This particular one is for concrete slabs above ground and walls. There's a different one for slabs on grade, and I think there's a third one as well. But this one seemed most appropriate, so I showed you this one. So this R value of 6. Let's keep that in mind. How do we get to an R value of 6? 306 has got different R values for different types of material. So this is for 1 inch of expanded polyurethane, got an R value of about 6.25. Expanded polystyrene, 4 to 5, glass fibers, 4, mineral fibers, so on and so forth. So if you've got 3/4 inch plywood as your formwork, you got about an R value of 1 right out of the gate. So this is good information. Also, if they're using blankets that are specifically for concrete, concrete curing blankets, most of them, I'll say the good ones, they've got tags on them, and these tags will say what's in it, and a lot of times these tags also give the R value. So take a look at the tag, see what the R value is, and if you need an R value of 6 and you've got maybe an R value of 1 from your formwork, and 1/2 inch, these blankets are about 1/2 inch, and maybe each 1/2 inch gives you 2 or 3 R value. Double them up, and you're getting to that 5 or 6 value that we would need for a 12-inch wall at 3 degree ambient air temperature. So we're up to question number 2. Another true-false question should read ACI 306.1. Those are the specifications, ACI specifications. Requires concrete that would be subjected to freezing during construction period to be air entrained. True or false?
The poll is closed. Back to you, Steve.
Hopefully everyone got that one. That is true. Something you wouldn't always consider, but should be considered. So here's another picture from Rivers Casino. We can see we've got two pier footings here being heated up. There's no concrete in here. They're just heating the enclosures to make sure that everything's thawed out, subgrades all thawed out. On one of the very first slides in this presentation, I mentioned planning. And if you look around, just a few things that you see. I mean, you see a whole bunch of blankets piled up over here. You see a heater right here. You see more blankets over here. This was, I want to say, early or mid-January. It's kind of hard to tell, but it's single digits out here, and yeah, that subgrade was pretty much rock hard. But they planned for it. Things went well. This is a pier after it was placed. You can see there's multiple blankets wrapped around it. You can see, very important, they've got the corners tied up right here. you know, so it's not blowing around or anything like that. You know, put multiple blankets on there, make sure the blankets are tied up nice and tight so they're not going to blow around and blow off. And again, just looking around here, you know, we can see good good planning with all the different equipment that they've got set up here. Here's another photo, same job. This is a foundation wall. It's I believe it was a 12-inch wall, multiple blankets on here. The other thing that's here that you didn't see in the other pictures was his glycol heating line. This placement was also heated using these using a glycol heater. But again, you can see it, they're tied up pretty good. You know, might flap around a little bit right here, but for the most part, it's on there pretty secure. This is an aerial view of the same project. I like this a lot because it really shows, you know, again, the level of planning that went into the project. This foundation wall, this is the same wall in the last photo that we saw. This is after the blankets have already been taken off, so this was probably a week later. But again, we see lots of good planning. We got lots of blankets here. You know, we got you know, these glycol heaters, you know, running out. We see these heating lines, and they've even got the heating lines covered up with blankets to retain the heat in those heating lines. What this contractor did was they just left the blankets in place until they needed them. You know, some of the blankets stayed on for over a week. So they just left them in place until they needed them. They had plenty of blankets. So good planning here. So one thing we want to do is avoid rapid temperature changes. We want to make sure that we're cooling gradually, so we're not you know, we're not inducing any kind of thermal shock. Concrete is it's kind of like untempered glass or ceramic, where, you know, it's susceptible to thermal shock, you know, if temperature changes too much too quickly. So we want to make sure that we're moving our heat slowly if we do have heat. Thermal blankets, take them off slowly, maybe one at a time, or again, maybe just leave them in place until the surface underneath kind of stabilizes with the ambient temperature. But we definitely want to avoid those rapid temperature changes. And both ACI 306.1 and ACI 306 reference the same thing, have the same recommendations and requirements. So these are the maximum allowable temperature drops within a 24-hour period at the end of your protection period. So this is after we've already protected it, our blankets are on, we were heating it, we were doing whatever we had to do to keep it within, you know, at that minimum 50-degree temperature. We don't just turn off the heaters and pull all the blankets off. But the allowable temperature drop is dependent on your section size. So you know, those, you know, that 6-inch slab or 8-inch foundation wall or something, you know, similar to that, less than 12 inches, you know, no more than a 50-degree temperature drop. You can see as the minimum section size gets bigger, the allowable temperature drop decreases. You know, these larger sections can really be more susceptible to thermal shock. So you want to make sure that you're not you know, you're not exposing them too quickly. And we're on to question 3. Should read, do we need to control the rate at which we allow the temperature to drop at the end of the protection period? I try to sprinkle the questions throughout the presentation rather than have them all at the end, hoping that I addressed them well and they're fresh in everyone's mind so they get the right answers.
All right, the poll is closed. Back to you, Steve.
So the answer is yes. Obviously, we do need to control the rate to avoid that thermal shock. So the prior table we saw 7.1. This is protection period. If what you're placing is going to see a full load within that curing period, it refers you to Chapter 8. Chapter 8 recommends doing different types of things, non-destructive testing, maybe field cured cylinders on that project at Rivers Casino in Schenectady. We did do some field cure cylinders. We didn't do field cured cylinders for every placement, but we did for quite a few of them. I think once they proved their curing methods and protection was adequate, we kind of started to get away from making those field cure cylinders. But in any event, it refers you to Chapter 8 to do different things. One of the things it mentions in Chapter 8 is the maturity method, ASTM C1074. And again, the maturity method is just a way to non-destructively estimate the concrete strength using basically time and temperature. So the primary concept of the maturity method says, it's a given combination of curing time and curing temperature, concrete temperature, results in a specific strength for a given concrete mixture. In other words, concrete strength is a function of time and temperature. I think we all know that. Colder temperatures, concrete strength develops much slower. Down below 40 degrees, there's a reason why 40 degrees is mentioned in both of the ACI documents. Below 40 degrees, cement hydration slows down significantly. And obviously right at about 32 degrees, it stops completely because your water turns into a solid and it just doesn't hydrate the cement. So we've got two different concrete maturity functions we're going to talk about, not in great detail, but we'll talk about them a little bit. The first one is the temperature time factor, and this is from some research that Nurse and Saul did back in 1951. It says a concrete of the same mix at the same maturity. And the maturity is just a product of time and temperature, has approximately the same strength, whatever combination of time and temperature go to make up that maturity. This is the time temperature maturity function. So you've got, this is your time temperature at age t. Delta T is your time interval in hours. You're measuring temperatures typically every half an hour, sometimes every 15 minutes. But T sub A is the average concrete temperature during the time interval, during that delta T time interval. So during that 15 minutes or half an hour, 1 hour, whatever your interval is. And T sub 0 is the datum temperature, which is the temperature at which strength development stops. Some people use 0. Most of this it's all in Celsius. Some people use 0 for datum temperature. The ASTM gives a little bit of guidance in the appendix on what to use, but 0, 1, or 2 degrees Celsius is pretty typical for a datum temperature. So you can see it's just a summation of all of the times and temperatures together. So there's your product of time and temperature. It's kind of the area under the curve. So the other maturity function is the equivalent age factor. And this is the number of days or hours at a specified temperature. So here we're keeping the temperature constant. Number of days or hours at a specified temperature required to produce a maturity equal to the maturity achieved by curing period at temperatures different from the specified temperature. couldn't really find a better way to word that, so I just worded it how they did back in 1977. But a good analogy is we're kind of comparing concrete cured in the field at different temperatures to concrete cured in the lab at a specified temperature. You know, we cure concrete in the lab either in tanks or in a cure room, you know, at about 68 degrees or something like that. So you know, this is could be a good way of comparing what you got in the field at different varying temperatures compared to what we've got in the lab. Here's the equivalent age function. It's based on the Arrhenius equation. If there's any chemical engineers out there, the Arrhenius equation, I believe, is a way of estimating the speed of a reaction, of a chemical reaction. And if you think about it, that's kind of what we're doing here, you know, with the hydration of the cement, you know, and the heat of hydration. So T sub E, that's your equivalent age in hours. Q is the activation energy divided by the gas constant K. T sub A is the average concrete temperature during your interval, delta T. T sub S is the specified temperature. That's the temperature that is remaining constant. Remember, that's, you know, that's our laboratory temperature, or whatever, you know, whatever temperature we're keeping constant. Obviously, this is not a linear equation. The previous equation is a little bit more of a linear type function. This certainly is not, with that funky exponential function in there. Some people say this does a better job of estimating the concrete strength at later ages, and the Nurse-Saul equation does a better job of estimating at earlier ages. The Nurse-Saul equation is probably the more common one. So we got the two equations. We kind of know what the what the idea is, right? You know, concrete strength is a function of time and temperature. So how do we apply that? What do we do with that information? You know, how do we use that in the field, you know, when it's 3 degrees outside or something like that, and you know, we need an idea of what our concrete strength is. It starts in the lab. You got to cast cylinders, at least 15 cylinders. It's got to be the same mix that's being used out in the field. So if you're using a 5,000 psi mix out in the field, this is the mix that we make in the lab and make these cylinders. We put maturity sensors in a couple of the cylinders, and then we start to test the cylinders. We're not testing the ones with the maturity sensors in them, obviously. We're testing the other ones. Either 2 or 3 if you're making 4x8 cylinders, get the average, and then test them at 1, 3, 7, 14, 28 days, maybe a little bit more frequently for a high early mix. We've done this at 2 and 4 hour intervals over 24 hours. So, loads can be applied, roadways can be opened up, things like that, for some high early mixes. And then you just plot the compressive strength and the maturity index. So each time you break a cylinder at 1 day, you're taking a reading off of the cylinders that have the maturity sensors in them. So you're getting that maturity value at the time you're testing the cylinder or cylinders, and you get a curve that looks something like this. You've got your maturity down here on the x-axis, and again, it's just a product of time and temperature. That's it. And then you've got your compressive strength, and you get a plot that looks something like this. And you apply this in the field by measuring what your maturity value is in the field. If you've got 10,000 degree hours in the field, that's what you measured in the field, then theoretically you've got about 4,000 psi on your on the structure. Again, we're doing this first in the laboratory. These are these maturity functions. Those graphs are specific to the mix. So after we do that in the lab, We can install the maturity sensors, in piers, footings, bridge abutments, whatever. Maybe at some critical loading locations. You want to avoid touching the sensors to reinforcement. You can tie them to the reinforcement, but just don't have them physically touching them. Usually there's the sensor itself is not touching the reinforcement, and then you just monitor the maturity index for strength gain, and then you just figure out what your maturity value is. Go to the plot and figure out what your estimated strength is. If you've got some critical operation that you're doing, maybe you want to consider some other things also. Maybe cores, maybe some other non-destructive method, Windsor probe, rebound hammer, pulse velocity. Maybe you've got some field care cylinders that you want to break or something like that. Again, this maturity method is just one of the ways. It's just one of the methods that's referenced in ACI 306. All right, we're on to question number 4. Should read, what are the 2 parameters that we measure for the maturity functions? Concrete strength is a function of blank and blank.
The poll is closed. Back to you.
Obviously, that's time and temperature. We've been talking about that for the last 5 or 10 minutes or so. Next question. Should also be a true-false question. The equivalent age maturity function assumes that concrete strength gain is linear based on time and temperature. That's the equivalent age. That's the one where we're keeping concrete temperature constant.
And the poll is closed. Back to you.
That is false. It's not linear. It is based on the Arrhenius equation. That's got that funky exponential in it. And that wraps it up. So we do have time to get to some questions if people have got questions.
We do have a question posed. The question was, can you explain whether there is anything additional that needs to be done with lightweight concrete? The aggregate has to be soaked prior to batching, and I am wondering if there's anything else that needs to be taken into account that would be different than normal weight. And this was from Adam Heisler.
That's a great question. A few years back, maybe closer to 10 years back, we did some lightweight concrete placements, and nothing additional was required. The aggregate does need to be soaked, otherwise that lightweight aggregate's gonna, believe it or not, it's gonna float up to the top. If it's not soaked properly. You would think because of the additional water and moisture that's in there that additional protection measures are needed, but that's really not the case. And a lot of times lightweight concrete has got even more cement in it, than a conventional mix. So that additional cement kind of, obviously adds an additional heat of hydration. So the answer is no, no additional measures need to be taken. We did on the same project, we had some of the curing blankets blow off within the protection period. And we had field cure cylinders because, it's just good practice during cold weather. And those field cure cylinders, they did show a very, very slow strength gain, but they did eventually make strength after 56 days. So it was definitely slowed down just because of the cold weather, but no long-term effects.
All right, we have another question. Where are the glycol heating lines typically placed while the concrete is curing? And this is from Chris Hannett.
Yeah, there's been a lot of discussion about that. I've seen some people put them in between two blankets. I don't know that that's really a good idea. The idea that, you don't want the heating lines right up directly against the concrete. I don't know of, I haven't read anything that says that the heating lines being in direct contact with the concrete is a problem, but the temperature could be a problem. I mean, some of those glycol heaters can go up pretty high. I mean, you don't want to turn the temperature up to 120 degrees or something like that. So it's more important to monitor the temperature of the glycol than where it's placed. And as long as you don't have your temperature too high, there's no reason why it can't be placed right up against the concrete.
All right, next question. How important is it to monitor the temperature of rebar prior to the pour as a function of curing? And this is from Kevin Guyon.
It's important that the rebar be above 32 degrees, and from what I've seen, that's the only requirement, is that it can't be. I think it reads that it can't be frozen, but as long as it's above 32 degrees, that's okay. There was actually some ACI research that was done. I think it was in Concrete International 2, maybe 3 years ago. That placed concrete with reinforcement at temperatures below 30 degrees. And some of them, I think, were down to 0 degrees or something like that. And the results were interesting. I won't spoil it, but yeah, they need to be above 32 degrees.
All right, and that is it for questions. We do have a couple comments, and I do want to address this. I apologize. The poll questions did not perfectly match up against some of the questions that you were reading, Steve. And I do apologize, guys. This was a disconnect. GoToWebinar does have a limit for the characters, so we had modified some of the questions so that they would make it to you in totality, and I do apologize. It didn't get back to be updated in the slideshow itself, but they were on theme. They were the same topic. So
okay.
Thank you, everyone who mentioned that, and I do apologize. All right, and it does not look like we have any further questions. So thank you, everyone. The webinar has now ended.